Now we will discuss nomenclature for ionic compounds. Ionic compounds can be divided into two categories, type 1 ionic compounds and type 2 ionic compounds. In all ionic compounds, the overall charge is zero. The difference between type 1 and type 2 ionic compounds depends on whether the cation has a consistent charge in all of its compounds. In a type 1 ionic compound, the cation always has the same charge. The charge of the cation is predictable based on its location on the periodic table. In a type 2 ionic compound, the cation can have multiple possible charges. Fortunately, the anion in an ionic compound always has a predictable charge, which allows us to determine the charge of the cation in a type 2 ionic compound. This periodic table shows the common charges that some elements form in ionic compounds. Metals tend to form positively charged cations, and nonmetals tend to form negatively charged anions. This occurs because atoms tend to gain or lose electrons to achieve the same number of electrons as the closest noble gas. For example, sodium can lose one electron to have the same number of electrons as neon, forming a 1 positive cation. Fluorine can gain one electron to have the same number of electrons as neon, forming a 1 negative ion. Because of these patterns, elements in group 1 typically form 1 positive cations, and alkaline earth metals in group 2 typically form 2 positive ions. Nitrogen and phosphorus in group 15 typically form 3 negative ions. Oxygen, sulfur, selenium, and tellurium typically form 2 negative ions. The halogens in group 17 typically form 1 negative ions. And noble gases in group 18 are unreactive and generally do not form ions. There is also a group of elements with predictable charges that form a triangle on the periodic table. This triangle includes silver, zinc, cadmium, aluminum, gallium, and indium. Silver is in group 11 and forms 1 positive ions. Zinc and cadmium are in group 12 and form 2 positive ions. And group aluminum, gallium, and indium are in group 13 and form 3 positive cations. The other metals not included in these patterns can have multiple possible charges. Type 1 ionic compounds contain cations with predictable charges. The cations shown here, along with ammonium, will form type 1 ionic compounds. If an ionic compound contains any other cation, it will be classified as a type 2 ionic compound. First, we will cover naming type 1 ionic compounds. Since the cation in type 1 ionic compounds always has the same charge, the charge does not need to be included in the name. The name of an ionic compound always consists of 2 words. The first word is the name of the cation, and the second word is the name of the anion. The ending of the anion helps us identify what type of anion it is. The suffix IDE indicates a monatomic single-element ion. A suffix of ATE or ITE indicates a polyatomic ion. For example, Cl- is called chloride because it is only a single-element ion. Chlorate is ClO3-, which is a polyatomic ion with 3 oxygen atoms, and chlorite is ClO2-, with 1 fewer oxygen atoms than chlorate. Earlier, we learned several polyatomic ions, ending with the suffix ate, ATE. Many of these ions have variations with different numbers of oxygen atoms, but the same overall charge. If a polyatomic ion has 1 more oxygen than the 8, the per prefix is added. For example, chlorate is ClO3-, while perchlorate is ClO4-. If a polyatomic ion has 1 fewer oxygen than the 8, the suffix changes from ATE to ITE. Chlorite, ClO2-, has 1 fewer oxygen than chlorate. If a polyatomic ion has 2 fewer oxygen atoms than 8, the hypo prefix is added along with the ITE suffix. Hypochlorite, ClO-, has one fewer oxygen atoms than chlorite. Polyatomic ions can also combine with hydrogen ions to form hydrogen-containing polyatomic ions. When hydrogen ions are added, the overall charge changes based on the original charge of the polyatomic ion and the number of hydrogen ions added. The name also includes whether one or two hydrogen ions is present. However, if we add enough hydrogen ions to make the compound neutral, the substance is no longer considered a polyatomic ion and instead becomes an acid. Here are some examples of type 1 ionic compounds. Our first example is NH4Cl. The cation is always written first in the chemical formula, and the anion is always written second. The cation is ammonium, NH4 with a 1 positive charge, which is a polyatomic cation. The anion is chloride, Cl-. We know that chloride has a 1 negative charge because chlorine is located in group 17. If we did not know the charge of the ammonium, we could have also determined it based on the charge of the chloride ion, because we know that the total charge of the compound must equal 0. To name this compound, we simply name the ions present. The compound is called ammonium chloride. The IDE suffix indicates that chloride is a single element ion. Now let's work in the opposite direction and determine the chemical formula from the name potassium carbonate. The anion is carbonate. The ATE suffix indicates that carbonate is a polyatomic ion. Carbonate has the formula CO3 with a 2 negative charge. The cation is potassium, which is located in group 1, and therefore has a 1 positive charge. To make the compound neutral, we need to have 2 potassium ions for every 1 carbonate ion. This gives us the formula K2CO3. Now we will move on to type 2 ionic compounds. In type 2 ionic compounds, the metal cation can have multiple possible charges, and therefore the charge of the cation must be included in the name. The charge is written using Roman numerals in parentheses. Let's review Roman numerals from 1 through 10. 1 is represented by a capital I, 5 is represented by a capital V, and 10 is represented by a capital X. For 2 and 3, we use 2 capital I's and 3 capital I's. 4 is written as IV because it is 1 before 5. 6 is VI, and 7 is VII. 8 is VIII, and 9 is 1 before 10, so it is written as IX. Let's look at some examples of type 2 ionic compounds. Remember that the anion always has a predictable charge, and we can use the chemical formula to determine the charge of the cation. For example, consider Fe2O. This compound contains 2 iron cations and 1 oxide anion. Oxygen will have a 2 negative charge. Since the compound must have an overall charge of 0, the 2 iron ions must provide a total charge of 2 positive. Each iron ion must therefore have a 1 positive charge. The name of this compound is iron 1 oxide. The Roman numeral indicates the charge of the iron ion, and the IDE suffix indicates that oxygen is now a monatomic single element anion. Next, let's convert the name copper to nitrate into a chemical formula. The Roman numeral tells us that copper has a 2 positive charge. Nitrate is a polyatomic ion with the formula NO3 1-. Since copper has a 2 positive charge, we need to have 2 nitrate ions to balance the charge. The chemical formula is Cu parentheses NO3 close parentheses 2. Here's a practice problem. Fill in the blanks in this table for the chemical formula of the compound, the cation's formula, the anion's formula, the name of the compound, and whether the compound is a type 1 or type 2 ionic compound. For the first row, we are given the chemical formula NaCl. This compound contains sodium ions and chloride ions. Sodium is located in group 1, so it always forms 1 positive ions. Because the cation has a predictable charge, this is a type 1 ionic compound. The name is the name of the cation followed by the name of the anion, so the name of the compound is sodium chloride. For the second row, we are given the ions Mg2 positive and ClO minus. Magnesium is located in group 2, so it forms a 2 positive ion. This makes it a type 1 ionic compound. The anion is hypochlorite, ClO minus. Chlorate contains 3 oxygen atoms, and hypochlorite contains 2 fewer oxygen atoms than chlorate. Since 2 hypochlorite ions will be needed to balance out the charge of the magnesium, the chemical formula is going to require parentheses. We will have Mg parentheses ClO close parentheses 2. The name of the compound will be the name of the cation followed by the name of the anion, magnesium hypochlorite. Next, we have the chemical formula FeO. Iron does not have a predictable charge, so this is a type 2 ionic compound. Oxygen has a 2 negative charge, so the iron must have a 2 positive charge to create an overall neutral compound. The name of the compound will need to include Roman numerals because it is a type 2 ionic compound. The name will be Fe parentheses II2 oxide. Next, we have aluminum 3 positive ions combined with oxygen 2 negative ions. Aluminum is part of the triangle of predictable charges, and it always forms 3 positive ions, making this a type 1 ionic compound. The name of the compound will be aluminum oxide, and the formula will be Al2O3. Lastly, we have nickel 3 nitrite. The Roman numeral tells us that this is a type 2 ionic compound. Nickel must have a 3 positive charge in this compound. Nitrate is a polyatomic ion ending with ITE. The ITE ending means that it has 1 fewer oxygen atoms than nitrate. Nitrite must have the formula NO2 minus. 3 nitrate ions are needed to balance the charge of 1 nickel 3 positive ion, giving this the formula Ni parentheses NO2 close parentheses 3. Lastly, we will briefly discuss hydrates. Hydrates are ionic compounds that contain water molecules. You can think of hydrates like sponges made from ionic compounds. The water molecules can be removed from the compound or absorbed back into the compound. The ionic compound is named using the same rules we have already discussed. The number of water molecules is then indicated at the end of the name. In the chemical formula, the water molecules are shown after a dot, and there's also a number to indicate how many water molecules there are. In the name, a prefix is used to indicate how many water molecules are present. Epsom salt is magnesium sulfate heptahydrate. Magnesium sulfate is a type 1 ionic compound with the formula MgSO4. The prefix hepta indicates that there are 7 water molecules, so the complete formula is MgSO4 dot 7H2O.